Ага, все вроде работает. Okay, so let's continue our discussion of approximate identities in C-star algebras. At the end of the previous lecture, we began proving an important theorem, which states that every C-star algebra has an approximate identity. So today, our first goal will be to complete the proof. Well, first of all, let's recall the definition of an approximate identity. If we have a normed algebra A, and here we have a net E lambda in A. So a net is something like a sequence, but it is indexed not necessarily by natural numbers, but by an elements of an arbitrary directed partially ordered set. And we say that this net is an approximate identity. Approximate identity, AI for short, if for every element A in our algebra, the net A E lambda converges to A, and the net E lambda A converges to A. So roughly, the idea is that an approximate identity is something which replaces an identity of a non-unital algebra. In fact, we have already seen that there are many natural examples of non-unital algebras, non-unital Banach algebras, which have approximate identities. So let's briefly recall that, for example, the algebra of continuous and vanishing at infinity functions, C0 of x, where x is a locally compact Hausdorff topological space, this algebra always has a bounded approximate identity. It is not unital, except for the case where x is compact. But if x is not compact, this algebra is not unital, but it always has a bounded approximate identity. The algebra of compact operators on a Hilbert space H is also not unital unless the space is finite dimensional. If it is infinite dimensional, then the algebra is not unital, but it has an approximate identity, actually a bounded approximate identity. They have bounded approximate identities. Moreover, if X is sigma compact, that is, if X is a countable union of compact sets, then this algebra has a sequential approximate identity, that is, an approximate identity indexed by natural numbers. And similarly, if H is a separable Hilbert space, then the algebra of compact operators has a sequential approximate identity. A slightly different example was the algebra little L1, considered with the pointwise multiplication. This algebra has an approximate identity, but doesn't have a bounded approximate identity. And actually another example, which I forgot to mention at the previous lecture, it's quite easy to produce examples of Banach algebras which don't have approximate identities. For example, if we take any Banach space A, then of course we can consider A as a Banach algebra with the trivial multiplication. That is, the product of any two elements is 0. Of course, this algebra doesn't have an approximate identity. Because the product of any two elements is 0. And a more interesting example, not so stupid, is the maximal ideal in the algebra of continuously differentiable functions. So A suppose that A is the algebra of those functions in the algebra C1 of continuously differentiable functions on the unit interval, such that f vanishes at 0. So this is a maximal ideal in C1, C01. Then it's a simple exercise to show that this algebra doesn't have an approximate identity. This is a nice exercise. So now we are going to prove the following result, which was stated at the end of the previous lecture. If A is a sister algebra, then there exists an approximate identity, E lambda, in A, such that this approximate identity has the following nice properties. First of all, well, let's denote this as condition AI1. AI is for the approximate identity. All elements in this net are between 0 and the identity in the unitization of A. So equivalently, this double inequality means that every E lambda is positive and sits in the unit ball, in the closed unit ball of A. So for positive elements, this condition and this condition are equivalent. This was proved at the previous lecture. And condition AI2 says that our net is monotone. If lambda is less than or equal to mu, then E lambda is less than or equal to E mu. So the proof first of all, let's recall that we have already constructed the index set lambda. So we denote by lambda the set of all positive elements in our algebra in the unit ball. So this is a partially ordered set with respect to our canonical order relation. And we have already proved the following claim, claim 1. This set lambda is order isomorphic to the set of all positive elements in our algebra. Now the isomorphism was constructed explicitly with the help of the functional calculus. So this result, this isomorphism, implies that lambda is directed, because the set of all positive elements is clearly directed. If you have two positive elements, then each of them is dominated by their sum. And since they are isomorphic, it follows that lambda is also directed. So now we can construct our net. Our net will be just the inclusion map of lambda into A. So this is a map which takes every element E in lambda to itself. And this is clearly a net satisfying both conditions AI1 and AI2. Just by construction. So now to complete the proof of our theorem, we have to show that this net is an approximate identity. The proof will be based on the following auxiliary claim, claim 2. So I claim that for any element, for any positive element A in the unit ball, we have the following convergence. A 1 minus E A goes to 0. So this net converges to 0. To prove the claim, we consider, we denote by T, the inclusion map of the interval 0, 1 into the complex plane. This is just the inclusion map. And we look at the following sequence, T times 1 minus T to the power 1 over n. It's a simple exercise in elementary calculus to show that this sequence uniformly converges to 0 on this interval. So it converges to 0 in the algebra C01. This is a simple exercise in calculus. We now apply the functional calculus of the element A, and we conclude that the following sequence, A times 1 minus A to the power 1 over n, converges to 0 in A. So for every positive epsilon, we can always find a natural number n such that the norm of this element, is less than epsilon. And now to show that our net, this net converges to 0, we take E in lambda. We take now any element E in lambda such that E is greater than or equal to A to the power 1 over n. So we have already found n, and we choose any E satisfying this condition. And we observe that then, of course, 1 minus A to the power 1 over n is less than or equal to 1 minus E. Oh, sorry, just the other way around. 1 minus E is less than or equal to 1 minus A to the power 1 over n. Yes? Yeah, this is true. And then observe that if we multiply these elements by A on the left and on the right, we still have the same inequality. Because, well, let's recall that we always have the following implication. If A is less than or equal to B, then X star AX is less than or equal to X star BX for all X. This implication was also proved at the previous lecture. This is one of the basic properties of the order relation on a C-star algebra. So this expression in brackets is less than or equal to this one, and we multiply by A on both sides. So A is self-adjoint because it is positive, and so we have this inequality. And therefore, the norm of this element is less than or equal to the norm of this element. Because the norm is a monotone function. If A and B are positive elements and A is less than or equal to B, then the norm of A is less than or equal to the norm of B. So we have this inequality. The norm of this element is less than or equal to the norm of this element because A sits in a unit ball. And this is so it is less than epsilon. So we see that for every positive epsilon, we have found an element in our net, that is in index, such that for any other element which is bigger than this one, we have this inequality. Just now we see that just by the definition of a convergent net, we have this convergence. This goes to 0. So this proves our claim. And now claim 3, this is our final claim. Our net, which is indexed by itself, is an approximate identity. To prove the claim, we take, again, any element A, satisfying this condition. Any positive element A in the unit ball. And let's try to estimate the norm of the element A minus EA. So we want to show that this goes to 0. So this is 1 minus E multiplied by A. For convenience, we calculate the square of this norm and apply the C-star axiom. So by the C-star axiom, this is equal to A 1 minus E squared A. The adjoint of this element is the product of these two elements taken in the opposite order. So we have this. And this is less than or equal to the norm of A times 1 minus E times A. So I can remove the square. Why can I remove the square? Well, because we always have the following inequality. 1 minus E squared is less than or equal to 1 minus E. And why do we have this inequality? This is immediate from the first Gelfand-Naimark theorem. Apply the first Gelfand-Naimark theorem to the C-star subalgebra of A plus generated by E and the identity. So this is, E is a self-adjoint element. This is a commutative C-star algebra. So it is isomorphic to the algebra of continuous functions on the compact space. And so what is 1 minus E? 1 minus E in this algebra is just a continuous function with values between 0 and 1. So clearly, you have a function with values between 0 and 1. This function satisfies this inequality. And so this holds in the bigger C-star algebra A plus as well. So this element is less than or equal to this one. And again, applying the same trick as here, we get this inequality. Okay, but by claim 2, we already know that this converges to 0. And so this one also converges to 0. So far, A was a positive element in the unit ball. But by linearity, we see that the same is true for any element in our algebra. A minus EA goes to 0 for every element in our algebra. Well, indeed, why is it so? Any element in our C-star algebra is a combination of two self-adjoint elements. It has a real part and an imaginary part. So we can write it as a combination of two self-adjoint elements. And a self-adjoint element is a difference of two positive elements. So every element in the C-star algebra is a combination of four positive elements. But for positive elements in the unit ball, we have this convergence. This implies that we have this convergence for any positive element. And by linearity, we have the same convergence for any element in our algebra, because it is a combination of four positive elements. So we have also to show that if we multiply by the opposite side, replace EA by AE, we still have the same convergence. But this is very easy. A minus AE can be written as A star minus EA star and again star. Here I'm using the assumption that E is self-adjoint. So this converges to 0, the involution is continuous, and so we see that this also converges to 0. And as a result, we conclude that E is indeed an approximate identity. And this completes the proof of our theorem. So from now on, we adopt the following standard convention. When we speak of approximate identities in C-star algebras, we always assume that, by default, we assume that our approximate identities satisfy the conditions AI1 and AI2. So from now on, an approximate identity means an approximate identity satisfying these two conditions. Okay. Well, of course, the approximate identity that we've just constructed is very big. It consists of all positive elements in the unit ball. But on the other hand, we have seen that in many concrete examples, like the algebra of continuous functions, say on the real line, or the algebra of compact operators on a separable Hilbert space, we can construct a more optimal approximate identity, which is sometimes sequential. And this is, in fact, a rather usual phenomenon. So I recommend you the following exercise. If A is a separable C-star algebra, if A is a separable C-star algebra, then A has a sequential approximate identity. Okay, so our next goal will be to discuss quotient C-star algebras. Let's start with some simple observations concerning quotients. First of all, some time ago, we have already observed that if we have an arbitrary Banach algebra, A is a Banach algebra, and the closed two-sided ideal, I in A, a closed two-sided ideal, then the quotient of A modulo I is also a Banach algebra. So let's recall that the standard quotient norm on the quotient is given by the following formula. This is the infimum of all representatives in this coset. That is, of all of the norms of all elements of the form A plus B, where B runs over the ideal I. Well, it's also rather easy to observe that if A is a Banach star algebra, this is is our second observation. If A is a Banach star algebra and I is a closed two-sided star ideal. So by a star ideal, I mean a two-sided ideal which is stable under the involution, such that for every element A, it contains the element A star. So in this case, the quotient is also a Banach star algebra. Is a Banach star algebra. And the involution is defined in the obvious way. That is by this formula. This is well defined because I is a star ideal. So now the natural question is, what if A is a C-star algebra? Can we claim in this case that the quotient of A modulo I is also a C-star algebra? The answer is yes, it is. But surprisingly, the proof of this fact is not entirely trivial. And the proof, which we will now give, is based on approximate identities. In fact, the proof is not obvious even in the case where A is unital. To prove this result, to prove that the quotient of C-star algebra is also a C-star algebra, we will need the following lemma. Suppose that A is a C-star algebra and I is a closed left ideal. Closed left ideal. I claim that I has a right approximate identity. A right approximate identity, AI, satisfying our standard conditions AI1 and AI2. This is AI1, this is AI2. So what do I mean by right approximate identity? Well, I mean that, well, let me write this down explicitly. This means that A E lambda converges to A for every A in I. That is, we multiply by E lambda on the right only, not on the left, but on the right. To prove the lemma, we consider the following set. We let B denote the intersection of I and I star. And let's observe that B is a C-star subalgebra of A. Well, indeed, it is a subalgebra because I is an ideal, so I is, in particular, I is a subalgebra. I star is also a subalgebra, and the intersection of two closed subalgebras is a closed subalgebra. So it is a closed subalgebra, but and it's also clear from the construction that it is stable under the involution. So it is a C-star subalgebra of A. And so it has an approximate identity. Let E lambda be an approximate identity in B. So again, B is a C-star algebra, and by default, we follow our convention. We assume that this net satisfies AI1 and AI2. I claim that the same net is a right approximate identity for I. Well, indeed, if we take an element A in I, well, let's estimate A minus A E lambda. We want to show that this goes to 0. So this is this can be written as A times 1 minus E lambda. Again, for convenience, I take the square of this expression, and we apply the C-star axiom, which gives us the following. This is equal to 1 minus E lambda times A star times A times 1 minus E lambda by the C-star property. Now, E lambda is somewhere in between 0 and 1. So the norm of this element in brackets is less than or equal to 1. So we can estimate this the following way: A star A times 1 minus E lambda. And this element A star A actually belongs to B. It belongs to I because A is in I and I is a left ideal. So it belongs to I. And it also belongs to I star because it is self-adjoint. And so it belongs to B. But E lambda is an approximate identity in B. And therefore, this converges to 0. And that's it. So we see that A E lambda converges to A. So this completes the proof of the lemma. And now we have the following theorem. Suppose that A is a C-star algebra, and I is a closed two-sided ideal of A. Then, first of all, I claim that I is automatically a star ideal. I is a star ideal. Every two-sided ideal, every two-sided closed ideal of a C-star algebra is a star ideal. Second, if E lambda is an approximate identity in I, then for every element A in our algebra, we have the following equality. The norm of the respective element in the quotient, that is the norm of A modulo I, is given by the following formula. It is equal to the following infimum: A minus A E lambda over all lambda. Or equivalently, we can replace the infimum by the limit. Limit of A minus A E lambda over all lambda. And finally, part 3, which will be deduced from part 2, the quotient of A modulo I is a C-star algebra. Okay, so let's start with part 1. Why is it a star ideal? So I is a closed two-sided ideal. In particular, it is a closed left ideal. So our lemma applies. So let's apply our lemma and deduce that there is an approximate identity, a right approximate identity E lambda in I. So therefore, for every element A in I, A E lambda converges to A. Now let's apply the involution, and we see that E lambda A star converges to A star because the involution is continuous. But this element, E lambda A star, belongs to I, because E lambda belongs to I, and I is also a right ideal. So this belongs to I. But I is closed, and this net converges to A star. So this implies that A star also belongs to I. And so we deduce that I is a star ideal. Okay, now let's look at part 2. First of all, if we compare this infimum and this infimum, we obviously see that, well, this one is less than or equal to this one, because AE lambda sits in I. So we clearly have the following inequality. This is less than or equal to the infimum over all lambda, A minus AE lambda. So this is trivial. Also, it's trivial that the infimum is less than or equal to the lower limit of A minus AE lambda. And the lower limit is less than or equal to the upper limit. So now to complete the proof, we have to show that the upper limit is less than or equal to the quotient norm. And if we prove this inequality, we will see in particular that the lower limit is equal to the upper limit, and so the limit exists. Well, let's take an element A in our algebra. Let's take an element B, so A in the algebra and B in the ideal. And let's try to estimate A minus A in lambda as follows. So this is A times 1 minus E lambda. So A is A plus B minus B. And by triangle inequality, we can write the following. Well, this is just the triangle inequality. So this expression goes to 0 because E lambda is an approximate identity in I, and B belongs to I. So this goes to 0, and this expression is less than or equal to the norm of A plus B. Because, well, this expression in brackets sits somewhere between 0 and 1. So the norm of this element is less than or equal to 1. Okay, so as a result, if we take the upper limit of A minus AE lambda, we see that this is less than or equal to the norm of A plus B, because this goes to 0. And since B was an arbitrary element in the ideal, we can now take the infimum over B over the right-hand side, and we deduce that the upper limit is less than or equal to the quotient norm, A plus I. This is true for every B, and so this, we have this inequality. If we now combine this and this, we see that these three numbers are actually the same. So we have this equality and this one. And in particular, we see that the limit exists because the lower limit is equal to the upper limit. Okay, now it remains to prove part 3. We have to show that the quotient is a sister algebra. Well, again, we take an element A in A. We look at the element A star A plus I. And let's recall that, in fact, we have to prove, it suffices to prove the inequality. Because, well, this was an exercise some time ago that if the norm of A star A is less than or equal to the square of the norm of A, then this automatically implies the C star axiom and automatically implies that the involution is isometric. We want to prove this inequality. we apply part 2. This is the following infimum. A star A times, oh, sorry, it will be more convenient to start with the square of the norm. Yes, with the square of the norm of the element A plus I. This way. And by part 2, this is equal to the following infimum. Okay. Now we apply the C star axiom. So this is the infimum over lambda. The joint of this element is the product of 1 minus E lambda and A star. So we get the following expression. Now 1 minus E lambda is between 0 and 1. So its norm is less than or equal to 1. And we can estimate this in the following way. A star A, 1 minus E lambda. So we just remove this element because it is in the unit ball. And again, we apply formula 2. And we see that this infimum is nothing but the norm of the element A star A modulo I in the quotient. So we have this inequality. The square of the norm of this element is less than or equal to the norm of this element. And we have already seen some time ago that this inequality implies that our quotient is actually a C-star algebra. A modulo I is a C-star algebra. And this completes the proof. Let's look at some useful examples of quotient C-star algebras. Example 1 is the so-called Kalkin algebra. Which was first introduced by James Kalkin in the 1960s, if I'm not mistaken, or maybe 1950s. We take infinite dimensional Hilbert space, H, and we denote by Q of H the quotient of B of H modulo the ideal of compact operators. Well, the compact operators is a closed two-sided star ideal, and we already know that the quotient is a C-star algebra. And this C-star algebra is called the Kalkin algebra. Of H. So our theorem implies that this is a C-star algebra. This algebra plays an important role in the extension theory of C-star algebras, which is closely related to, to K-theory and to K-homology of C-star algebras. Another important example, example 2, is the Toeplitz algebra. So to define this algebra, we take, again, a Hilbert space. So H is an infinite dimensional separable Hilbert space. We choose an orthonormal basis, En, for convenience, it will be indexed by non-negative integers and of normal basis of H. And we consider the right shift operator, S, on H, the right shift operator, which is uniquely determined by the following rule. It takes En to En plus 1. Clearly, there is a unique bounded linear operator on H satisfying this condition. It is called the right shift operator. And now we define the Toeplitz algebra to be the C star subalgebra of B of H generated by S. Generated by S. So this is the smallest C star subalgebra of B of H containing the right shift operator. Explicitly, this algebra can be described as follows. Let's denote this subalgebra by T calligraphic. So this subalgebra T is the closure of the linear span of all monomials of the form S to the power K times S star to the power L, where K and L are non-negative integers. Well, why is it so? This is true because it's very easy to check that S star S is the identity map. In fact, this equality is equivalent to the fact that S is an isometry. It preserves the norm. So this product is 1. And so if we take the C star subalgebra generated by S, we know that in the general case, it is the closure of the linear span of all non-commuting monomials in S and S star. So in the general case, you have to consider finite products of the form S to the power K, then S star to the power L, then again S to the power, say, M, and then again S star to another power N, and so on. But because of this condition, every non-commuting monomial in S and S star can be simplified to this form. So as a result, we see that the Toeplitz algebra is equal to the closure of the linear span of all such operators. The Toeplitz algebra is a rather important object. Like the Kalkin algebra, it is important. It naturally appears in K-theory of C-star algebras. And in particular, it is an essential ingredient of one of the most elegant proofs of the Bott periodicity theorem given by Kuntz. The terminology of this algebra is called the Toeplitz algebra because it is somehow related to Toeplitz operators. But today I'll not tell you anything about Toeplitz operators. This is not so important for our purposes. And Toeplitz operators are related to Toeplitz matrices which were studied by Toeplitz. So Toeplitz didn't know anything about Toeplitz algebra and about Toeplitz operators. He considered only matrices. But later, some people generalized Toeplitz matrices to Toeplitz operators. And finally, they were incorporated into the Toeplitz algebra. Okay, so how is this related to our discussion of quotients? I recommend you to look at the following exercise. First of all, it turns out that the compact operators, the set of compact operators is contained in the Toeplitz algebra and is a closed star ideal. of T. A hint is to show that by using operators S and S star, show that all matrix units with respect to our basis belong to the Toeplitz algebra. And linear combinations of matrix units are dense in the ideal of compact operators. So all compact operators are contained in Toeplitz algebra. So what if we construct the quotient of T modulo KOH? I claim that this is isomorphic to the algebra of continuous functions on the circle. So T is just the unit circle on the complex plane. Here the hint is as following. It can be shown that this quotient is a commutative algebra. So all commutators of elements in T actually are compact operators. So the quotient is a commutative algebra generated by a single element, the coset of this operator, of the shift operator S. So it is isomorphic to the algebra of continuous functions on the spectrum of this single element. And the spectrum of an operator considered modulo the ideal of compact operators is the essential spectrum. And now everything is reduced to the fact that the essential spectrum of the shift operator is the circle. So as a result, we get the following exact sequence. So the ideal of compact operators is contained in the Toeplitz algebra, and the quotient is isomorphic to the algebra of continuous functions on the circle. This is the so-called the Toeplitz extension. Toeplitz extension. And the exercise is to show that the Toeplitz extension doesn't split. Doesn't split, which means that there is no star algebra homomorphism, say J, from C of T to the Toeplitz algebra, which is a section for P, such that Pj is the identity map. A hint to this part of the exercise is to use the Fredholm index, which is quite natural because after we quotient out the ideal compact operators, we obtain something which is closely related to Fredholm operators and to the index. Okay, so these are two natural examples of quotients. The Kalkin algebra and the quotient of the Toeplitz algebra modulo the compact operators, which is isomorphic to the algebra of continuous functions on the circle. Okay, so we still have some time. Now let's come back to positivity in C-star algebras. We already know what positive elements are, and let's now discuss positive functionals. Positive functionals on C-star algebras. So we start with the following situation. We take a star algebra A, an arbitrary star algebra, not necessarily C-star algebra, and a linear functional f on A. A linear functional f on A. We say that f is positive and write the following expression. If f satisfies the following condition for every a in A, the following number is non-negative. If, moreover, we know that A is a Banach star algebra, if A is a Banach star algebra, then a continuous linear functional f on A is called a state. State if it is positive and the norm of f is 1. The Russian for state is состояние. States, that is positive functionals of norm 1, naturally appear in quantum mechanics. Maybe I'll tell you a little bit more about this later. And for our purposes, states are important because, as we will see soon, they are closely related to representations of C-star algebras. If we now assume that A is a C-star algebra, then let's recall that elements of this form are positive. And moreover, every positive element can be written in this form. So we see that, we observe now that if A is a C-star algebra, then a linear functional f on A is positive if and only if it takes positive elements to non-negative numbers. Okay, let's now look at some examples of positive functionals. Example 1. If chi is a star character, then clearly chi is positive. For a simple reason that chi of A star A is just the absolute value of chi of A squared. And this is non-negative. Moreover, if A is a C-star algebra, and chi is a non-zero character, then chi is a state. This is a little exercise here. It's clear that the norm of chi is less than or equal to 1, but it's rather easy to show that this is exactly 1. Для C со звездочкой алгебры, да. Это мы доказали. А для произвольной звездочки алгебры не обязательно. So here, in the first part of this example, we don't assume that A is a C-star algebra, just a star algebra. But indeed, for C-star algebras, we know that every character is a star character. Okay, example 2. Suppose now that A is the algebra of continuous and vanishing at infinity functions on a locally compact Hausdorff topological space X. In other words, an arbitrary commutative C-star algebra. And suppose that mu is a finite positive Radon measure on X. Then mu generates a positive functional f mu on our algebra by the following simple formula. It is just the integral with respect to mu. Then clearly f mu is a positive functional because the integral of a non-negative function is greater than or equal to 0. It is a positive linear functional, and its norm is just the measure of x. Again, this is a little exercise in measure theory to show that the norm is exactly the measure of x. So in particular, we see that it is a state if and only if mu is a probability measure. And in fact, this example describes all positive functionals on C0 of x because we have the following classical result, which is called the Riesz representation theorem. And it is due to many people: Riesz, Markov, Kakutani, and many other authors. So originally is what proved by Riesz in the case where x is an interval on the real line, but later it was generalized to more general spaces by many authors. So Riesz, Banach, Sachs, Markov, Kakutani, Shmuryan, so many of them independently proved this result. So this theorem states that we have a bijection between the set of all finite positive Radon measures on x and positive linear functionals on C0 of x. And this bijection takes every finite positive Radon measure mu to the functional f mu, which is given by integration with respect to mu. So we see that if A is a commutative sister algebra, then positive functionals bijectively correspond to finite positive Radon measures. And so morally, for an arbitrary sister algebra, positive functionals can be viewed as non-commutative generalizations of positive Radon measures. We assume that it is finite. We consider only finite measures. If it is not finite, then we cannot define this functional on all C0 functions. Like the Lebesgue measure on the real line, there are many natural examples of C0 functions on the real line which are not integrable with respect to Lebesgue measure. Of course, it is essential that it is finite. Okay, another example, example 3. Example 3. Let's take the algebra of square n by n matrices. Well, it is a finite dimensional sister algebra. It is isomorphic to B of H, where H is an n-dimensional Hilbert space. So we have the following standard example of a state on this algebra. The so-called normalized trace f of t is 1 over n times the trace of t. The normalized trace. So it's easy to show that this is a state. Is a state of A. This is example, well, an example and an exercise at the same time. But this is a simple calculation to show this is indeed a state. In fact, it's rather easy to describe all states on the matrix algebra. To do this, let's observe that for every linear functional f on A, there exists a unique S in the same algebra such that f of A, as denoted by fs of A, is the trace of the product AS. So this result is sometimes referred to as the trace duality. The trace duality between the algebra A and itself. So the trace duality is established by the trace. Part 3, this functional fs is positive if and only if the operator s is positive. And it is a state, fs is a state if and only if s is positive and the trace of s is 1. So this result describes all states on the matrix algebra. Okay, let's now look at something infinite dimensional. Example 4. We take a Hilbert space H, a Hilbert space, and let A be the algebra of all bounded operators on H. Then for every vector xi in H, we can consider the following functional xi on A, given by the following formula. Xi of t is the inner product of t xi and xi. Clearly, this is a linear functional, and it's easy to see that it is positive if we apply it to t star t. So we substitute t star t here. We move t star from here to here, and we get the inner product of t xi by itself, which is non-negative. So this implies that f xi is a positive functional. And also it's easy to see that the norm of f xi is equal to the norm of xi squared. So in particular, we see that f xi is a state if and only if the norm of xi equals 1. States of this form are often called vector states. A vector state on BOH. Because it is determined by a vector. Well, let me say a few words about the terminology and also why states are so called. The terminology comes from physics. Actually, there are two fundamental notions in classical mechanics and in the quantum mechanics. States and observables. In the mathematical model of the classical mechanics, states are just points of a smooth manifold, which is interpreted as the phase space of a mechanical system. So states are just points, and observables are real-valued functions. Usually we consider smooth real-valued functions on this manifold. So these are states and observables in the classical mechanics. In quantum mechanics, the situation is different. In the mathematical model of quantum mechanics, states are vectors on the unit sphere of Hilbert space. That is, vectors satisfying this condition. And observables are self-adjoint operators. In general, they are not assumed to be bounded, possibly unbounded self-adjoint operators on this space. And this expression, this inner product of t xi and xi, is interpreted as the mean value of the observable t in the state xi. So states of this form are sometimes called pure states. There are also so-called mixed states in quantum mechanics, which are defined similarly to our example 3, that is, with the help of this formula. But of course, in order to make sense of this expression, we must impose some conditions on S. So in the general case, the trace is not defined on all bounded operators. But if S is a nuclear operator, or the so-called trace class operator, then this is well defined, and we get a big family of states on B of H, the so-called mixed states. And they also have some natural quantum mechanical interpretation. Okay, another example. Another example of a state comes from group C-star algebras. This is example 6. Oh, sorry, this is example 5. Example 5. We start with a group. Again, this is an example and an exercise at the same time. We take a group G, and we consider the following functional f on the Banach algebra L1 of G. So we know that L1 of G is a Banach star algebra in a natural way. F is just the evaluation at the identity of the group. Here is the identity of G. So prove that, first of all, that F is positive. And then prove that F, well, actually, F is a state. It's easily seen to be a state on L1 of G. As a state. And second, F uniquely extends. Uniquely extends to a state that is denoted by F tilde on the reduced group C-star algebra, C-star R of G. Well, the reduced group C-star algebra was discussed some time ago as an example. It is defined to be the closure of the range of the regular representation of L1 of G. And moreover, it can be shown that F tilde is actually a vector state. Okay, let's now prove something interesting about states and about positive functionals. Oh, this will be our last result for today. So we have the following proposition. Suppose that A is a C-star algebra, and F is a positive linear functional on A. Then, first I claim that F takes self-adjoint elements of A to real numbers. Second, I claim that F is Hermitian in the sense that it is compatible with the involution. So we have this formula for every element in our algebra. And finally, I claim that F is automatically continuous. So we didn't assume the continuity in our definition of a positive functional, but it turns out that positive functionals on a C-star algebra are automatically continuous. So this is another useful automatic continuity result. We already know that all characters on the Banach algebra are continuous. We know that all star homomorphisms between C-star algebras are continuous. And now we will see that all positive functionals on a C-star algebra are continuous. Well, part 1 is very easy. Part 1 is very easy because if A is self-adjoint, we can write it as a difference of two positive elements. We know that A can be written as A plus minus A minus, where A plus minus are positive elements. And this readily implies that f of a is real. Because f of a plus is positive and f of a minus is also positive. The proof of part 2, so 2 actually follows from 1. 2 follows from 1. And this can be proved by the same argument as in the case of characters. Some time ago we proved that every character of a C-star algebra is a star character. But actually, to prove this, we used only the fact that a character takes self-adjoint elements to real numbers. So I'll not repeat this argument, just look at the proof. See the proof for characters. So look at the proof for characters and observe that the same proof works for arbitrary positive functionals because they satisfy condition 1. And finally, let's show that f is continuous. First of all, I claim that f is bounded on positive elements. There exists a constant c such that for every positive element a, we have the following inequality. F of a is less than or equal to c times the norm of a. Why is it so? Well, if this is not the case, then for every natural number n, we can find an element, a positive element an, such that the norm of an is less than or equal to 1, but f of an is greater than or equal to, say, 4 to the power n. And let's now consider the following element will be the sum of an over 2 to the power n. Obviously, the series converges because the norm of a1 is less than or equal to 1. A is a positive element because the set of positive elements is stable under the sum operation and it is closed. So a is positive. So what can I say about f of a? F of a is greater than or equal to f of a n over 2 to the power n for every n. Because f is a positive functional, and the positive functional is clearly monotone. A is greater than or equal to the nth term of the series, and f is monotone. So we have this inequality. But because of this, we see that this is greater than or equal to 2 to the power n, and this is true for all n, which is clearly impossible. This is a contradiction. This is a contradiction. So the contradiction implies that we have this formula. There exists a constant c such that f is bounded by c on positive elements. Now, to prove that f is bounded in the usual sense, that is everywhere on A, we take an element A in our algebra and write it in the form B plus IC, where B and C are self-adjoint. And each of them is the difference of B plus and B minus. So B can be written in this form, and C can be written in this form. Now, so B is, what is B? B is A plus A star over 2. So this implies that the norm of B is less than or equal to the norm of A. And for the same reason, similarly, the norm of C is less than or equal to the norm of A. Because C is, C is A minus A star over 2I. And so for the same reason, its norm is less than or equal to the norm of A. Also, it follows from the construction, if we now recall the explicit construction of these two elements, B plus and B minus, they are obtained with the help of the functional calculus. It follows that the norm of b plus and of b minus is less than or equal to the norm of b. And similarly, the norm of c plus and c minus is less than or equal to the norm of c. So as a result, we see by applying the triangle inequality that the absolute value of f of a is less than or equal to the norm of this plus the norm of this plus the norm of this plus the norm of this. So in summary, we see that this is less than or equal to the 4 to 4c times the norm of a. And therefore, f is bounded. F is bounded. That is continuous. And this completes the proof. Okay, so that's all for today. At the next lecture, we continue discussing positive functionals. We'll prove a useful positivity criteria for the linear functional. And we apply this result to showing that every positive functional defined on a C-star subalgebra can be extended to the whole algebra. And this extension result will eventually enable us to prove the second Gelfand-Dynamo theorem, which states that every C-star algebra can be isometrically embedded into the algebra of bounded operators on a suitable Hilbert space. Okay, thank you. On a suitable Hilbert space. Okay, thank you.